Hello and welcome to CE 3105 Lab 6 Impact of Jets. So far we've been looking at basic fluid properties in the lab, and then over the last few weeks we spent considerable amount of time looking at flow through pipes as well as the conservation of energy equation in conjunction with our continuity equation. So we'll continue that discussion and look at jets, which are specialized streams that have a wide range of civil engineering applications. So we'll begin our discussion with defining what a jet is. A jet is simply a stream of fluid that's projected onto a surrounding medium. So here I show a jet of water being projected out of that nozzle into the surrounding medium. So nozzles are really small diameter openings. They are pipes with very small openings and that are used to create jets. So as the diameter goes down, you know that the velocity goes up. So the water or the fluid that's leaving the nozzle has very high velocity, and that high velocity causes it to be in inertia and cause that water to move further along against the force of gravity for a certain distance before gravity takes over and it starts to fall back. Okay, so jets have a wide range of applications. So whenever we want a high velocity stream of water or fluid, we make use of a nozzle and get a jet created, a jet of water or jet of fluid created. Jets have a wide range of applications. As I said, aeration of wastewater. So we actually put a jet of air through wastewater in order to increase the oxygen content in that wastewater, which in turn can be used for microbial growth, which in turn helps clean up that wastewater. So jets are used extensively in environmental industry for aeration. They are used in construction industry for cutting and cleaning operations, so washing out fines and things like that. We make use of jets of water, and also for cutting certain things. We can use jet of water for cutting out slabs and such. Another very important use of jets is with impulse turbines. Basically, we have a jet hitting the blade of the turbine, which causes the turbine to move, and then the movement of the turbine causes the mechanical energy, which in turn is converted into electrical energy, and that's what turbines do. Jets are also being seen as a water conservation strategy. So these days we see taps instead of producing as a stream of water, produce a jet instead. So we get lesser water, but we get more efficient use of that water because we can clean better with the higher velocity fluid than we could with a larger volume of water moving at a lower velocity. So in addition to these engineering applications, jets also occur naturally. Spring discharges are one places where you will see jets. Similarly, turbulent jets can be caused. You can find turbulent jets in streams and rivers during flooding, and these turbulent jets can cause scouring of soil and affect foundations and bridge piers. Um, so even from a structural standpoint or a geotech standpoint, understanding what the forces associated with jets are important to evaluate the structural integrity of certain structures. So as you can see, environmental, water resources, structures, geotech, construction. So jets find a wide variety of use throughout civil engineering. So to assess, to understand jets, so what we are really interested in is we use jet, and that jet comes out of a nozzle. Let's say that the velocity of the jet exiting the nozzle is equal to u. And because of inertia, the jet keeps moving, or that stream of water or fluid keeps moving, and it hits a vein. A vein simply is an obstruction. This could be an impeller blade. This could be a wall that we want to wash, whatever be it. So vein is simply a structural obstruction that this jet is going to impinge upon or going to hit, and we'll assume that this vein is at a distance s from the nozzle. So So we can write the conservation of energy equation and say that the energy at the nozzle, which is here, so again, this is open to atmosphere, so our gauge pressure is equal to 0. And if we make this our datum, like, so if we assume that the nozzle is our datum, so then we also have no potential energy term here. So the energy of the nozzle is equal to the kinetic energy, which is equal to half m dot u squared, m dot being the basically the fluid mass flow rate, and given as the density times the volumetric flow rate Q, which we have been measuring in the lab. And that is equal to half m dot u squared. U naught is the velocity with which the water or that fluid is going to hit that vein, plus the potential energy term because of the movement of water from the datum to a distance s. So that's m dot gs. So if I rearrange this, I can calculate the velocity with which the water is going to hit that vein, or the fluid is going to hit that vein, which is equal to u squared. U sub naught squared is equal to u squared minus 2gs. And if I take square root on both sides, I can calculate this velocity u sub naught. Okay, so once we have that, the vein, so now we start our focus and look at what happens right at that vein, or right at that obstruction. So when the water hits that vein, or when the jet hits that surface, there is a considerable loss of energy. So we can't make use of Bernoulli's equation anymore. And as a result, we will switch to conservation of momentum. Conservation of momentum because momentum is always conserved. And we say that the rate of change of momentum, which is equal to the force that's experienced by the vein, is equal to the momentum that's coming in minus the momentum that's leaving the system. So what is the amount of momentum that we are delivering to the vein, and how much is the momentum that we are delivering out of the vein? And we can write equations for that. And we say F is equal to m sub naught u naught. That is our momentum being delivered in, and m dot u1 cos beta is the momentum that's being delivered out. So this is looking at forces that are acting on the vertical plane of that vein. So I can, if I assume that u naught is approximately equal to u1, or u1 is approximately equal to u naught, then I can factor out that m dot u naught term and write that the force is equal to m dot u naught 1 minus cos beta. So this is our theoretical expression for the force that's acting on the vein. And in our experiment, what we want to do is we want to experimentally determine what that force is that's acting on the vein, and then compare it to theory. So what I show here is I have a vein, which here is a flat plate, and then I have a nozzle. The water comes in and from the reservoir travels, and as the cross-sectional area goes down, the velocity goes up, and there is a jet that is shot out of that nozzle, and then it hits the vein, and then it moves away, like in a perpendicular to the direction of the flow, or normal to the direction of the flow. Because of the force of this vein, because of the force of this water, the vein starts to move up. And what we do is we counterbalance that force using a jockey weight. So we move this jockey weight till this cantilever scale is back to being parallel to the ground surface. And then we can apply moment. We can take moments right around that edge there, like right around that edge. We take the moments and we say that the force, this is the force of water that's acting on the vein, times the distance A, which is shown as this white line here, and that's given to you as 15 centimeters in your experiment, is equal to the mass times the acceleration due to gravity, which is the weight of the jockey times a plus y. So the two forces, or the moments generated by two forces, one in the counterclockwise direction and one in the clockwise direction, balance out once this cantilever is parallel to the ground surface. And from there we can calculate experimentally what that force is by multiplying the mass of that jockey weight, which is given to you in your lab handout, times the acceleration due to gravity times a plus y divided by a. So that's how you get the experimental force, and then we compare it to the theoretical force based on the theory of impulse momentum equation that I showed you in in the previous slide. So we make use of, we'll see how good our experiment matches the theoretical result. So to do the experiment, we'll do it for two different types of vanes. One is the flat plate, the other one is the hemispherical plate. And the flat plate has a beta of 90 degrees and the hemisphere has a beta of 180 degrees. So the theoretical force is given as m dot u naught and 2 m dot u naught. Again, u naught we can calculate based on conservation of energy, and m dot is simply your mass flow rate, which is density times the volumetric flow rate. So what we do is we start off our experiment, we zero the cantilever scale to make sure that it's parallel to the ground surface. And then we turn on the flow, and we have the flow moving in. The flow causes the jet to impinge water on this vane, which causes this plate to move. So we're going to move this weight and make sure that it balances or counterbalances the moments. So the moments are equal at that point. And then you get the mass, the distance, the required distances from our handout, and then we measure the flow rate volumetrically. This time we are going to use the reservoir that's out here to measure our flow rate. And once we have the flow rates, we repeat this. We change our flow rate and repeat the experiment 6 times for each vane. So we have 2 different vanes, and then we get 2 different set of experiment, 2 different set of values, and from there we calculate the experimental force and then compare it to the theoretical force. So that's all there is to this experiment, impact of jets. And the impacts of jets. The goal of this experiment is to get you to learn about impulse momentum equation and use of conservation of momentum and continuity equation to get the forces associated with jets of water. Thank you.